Actually. So in today's class, we are going to see the first fundamental form, and first fundamental form is related to something. Suppose if you want to calculate surface area, or suppose if you want to calculate the length of the curve, fundamental form is important for those kind of things. Okay. And this formula is little generalization of whatever arc length or surface areas and all those kind of things which we calculate in our usual calculus course. Okay, so we have to see what is this form is. See, in general, those who know little bit of differential geometry or manifold theory, they must have heard about this form. Have you heard about this form, Swaroop? Any differential form? This word before?
Yes, ma'am.
Differential form. Yeah. What is it?
Ma'am, I forgot.
Okay, fine. So see, differential forms are related. I'm sorry. So differential forms are related to dual tangent space, and it is and then actually what we do is we take something called exterior product of it, and then we can form actually even more. But right now, for our purpose, the first fundamental form is just a one form. So we are going to deal with a dual of a tangent space. That is what we are going to do. So we don't need to really go into the theory of differential form. So right now, what we are going to do is we are just going to look at this functional. So these are maps from TPS to that of R. And then we will see how it can be helpful to us to calculate these curves over the surface. Okay, so that's what we are going to do it. And we will do all this construction over by assuming one surface patch, because what we are going to do is, I mean, that is sufficient. If you have two surface patches, then there is some kind of changes are there, but they are just linear changes. So we will fix one surface patch and we will be working on that. So let me start it. Right. So let S be a so we are fixing our surface, here surface, and we are also fixing our surface patch. Okay. So and this sigma, this is a map from U to S, be a surface patch. And this is again, we will first define it point wise and then I'll tell you how it is function wise. So let us fix also a point. Okay. So let sigma be a allowable, let me write it, an allowable surface patch first time, then later I will drop the word, and allowable surface patch. And I want to take a point P belongs to S, which is inside this image. So, so this P, this is belongs to sigma of U. So P is equal to some sigma of U naught V naught. For some point, this U naught V naught belongs to U. So this is our basic, we are going to fix our notations. Okay. Then what we know about this thing? So this is our first point. Okay. So whenever now we are talking about, as I said, fundamental form is a dual space of tangent space. So let us recall what we have done it earlier for the tangent space. So let me just tell you what is this. So what we have so far, what we have done is, if I have all this information is given to me, then in that case, I know that if I take a tangent space at a point P for the surface, then can you tell me what is the basis for this?
Sigma U and sigma V.
Right. Don't sorry, tangent plane. See, don't whenever we are talking about this sigma U at a point U naught V naught, let us say it, because if you take a sigma U now, this is going to be a function actually, right?
Yes, ma'am.
Okay, right. But anyway, I'm also going to drop this notation. So, but let us first time write it. Okay. So then these two vectors, they are going to form a basis for our this tangent space. And we will drop this notation. So let me write it. Okay, so this is what which we have done it, and now actually on this I want to build up something. So let us actually do this one thing. So let us define this linear map from this TP of S to that of R. What is this map is? This is actually du of W is, it is a cu, this I'm now dropping the notation, so of W. Okay, so see sigma u, this is a this is okay, right? Sigma u star of W means what it will be? Suppose if this W, since this is a basis, this is going to be of the form lambda times sigma u plus mu times sigma v, right? So sigma u star means it will take this coefficient, right? Is that okay? So this is, we are going to denote by, rather than denoting by sigma u star, we denote it by du. This is a standard notation, okay? So because of that, this du, this is an element, this is a function of, this is an element of TP star. Those who knows actually differential form, for them I'm writing this. So this is an element of TP star, which is generally called cotangent space, okay? So this is called cotangent. Okay, and then similar to this du, of course, we can define dv also. There is nothing. So what is dv is? This is again. So dv of w is equal to sigma v star of w, which is equal to mu. Okay, so these two functionals which we have defined it just now, and now actually we will we what we want to do is we want to do inner product on TPS. Okay, that's what we want to do is. So what we want to do is, not define it actually. So, but let me just take it. So suppose if U belongs to this TPS, where is this tangent space? It is a plane inside R3, right? And on R3 we have an inner product. Usual standard inner product is there. No? That's what I'm talking about. So now actually with this, what can you say about now this, what will be norm of this square?
Inner product of W.
Right, but what is the W is? W is this, right? So this is a lambda times sigma u plus mu times sigma v, lambda times sigma u plus mu times sigma v. So here actually what are these sigma u and sigma v? They are vectors. And this lambda and mu, what are they? They are actually a scalars R. And what we know about inner product? Inner product is bilinear, right? So what is this expression will give me? This will give me lambda square times norm of sigma u square plus 2 times lambda mu times sigma u dot product with sigma v. Okay, dot product, I didn't find it like this, right? Let me write it. Plus lambda square times norm of sigma v square. Is that okay? Srinanda, is this fine? Srinanda Pooja?
Yes, ma'am, that
I just
at the end.
Oh, sorry, right, correct. That is new. Thanks, sir. Right. But what is this lambda is? Lambda is a du, no? So let us write that. So what is this actually? This is a norm of sigma u square times du. Oh, can you just give me a minute? I think my pen battery is over. Satya, maybe you just stop for a minute. I have to change my battery. Okay, so and if you notice here, what is this sigma u, this norm of this sigma u square that is independent of w, right? Is that okay for you? In this expression, what are the elements which are independent of w? What are the numbers which are independent of w?
Sigma norm of sigma u and norm of sigma v.
Right, exactly. So all of those numbers, they are actually independent of our right. So the what is happening? Okay. Right. So these are actually numbers which are independent of a W. So let me write them as a some constant. Okay. So standard notation is E. So what is E is? It is, we denote it by sigma U square because it is independent of W. Then we write F as inner product of sigma U sigma V, and we write a G to be equal to norm of sigma V square. Okay. So because of that, this norm of W square, what you got it? You got it as a du of W square times E plus 2 times F of du dV. This, let me write it as a, okay, so these are also numbers, sorry. So I can just write du dV plus G times mu square, right? And where is this number is? This number is, no, not mu square. What is this? dV square, right? dV, okay, sorry. So what is this? Lambda is du of W, mu is dV of W, and then plus mu squared plus G times dV of, what is this? dV of W, okay, whole square, right? So now if so, and what is this? This is from where to where? Actually, we are going from TP of S to R. Is this okay?
Yes, ma'am.
For every W, we are defining like this, right? Right. So now actually, if I remove this W, then I'll get a function, right? So I'll get a function which is of this form. TPS to R. Okay. So as I said, any function which is, so what is this? This is the element of TP of S star, right? So it is inside dual space. So anything which goes inside dual space, it is, we call it as a form. And this is a very specific form. So this form, we will call it as a first fundamental form. So what is the definition is? So let me write it as a definition. So in fact, if anything which is related to dual space of, I mean, if it is an element of dual space of tangent space, then we call it as a one form because it has a degree 1. And then later on, what we do is we kind of, we also define 2 forms and 3 forms and so on. Okay, so let me write it as, so this E du square plus 2F du dV plus dV square. Did I missing something? G is missing here, right?
And G is missing.
Yeah. So G here. G times dV square is called the first fundamental form. So if you notice here, it is depends upon something, right? What is it depends upon?
The surface patch.
Right. So we will write it like it is a fundamental form of surface patch. Okay. So let me just write it first. It's called a first fundamental form. Okay. So let us see first example. Sorry, not only here. So first fundamental form of first fundamental form with respect to of the of the surface patch. So it is, as I said, it is depends upon surface patch. So patch sigma UV. Okay, but actually it is not quite depend. Yeah, the first fundamental form, though its definition looks like means if you choose another surface patch, their relation is just depends upon Jacobian. Okay, that is one of the exercises there. We will see it in one of our tutorial. Okay, it is not just a symmetric, so it is not very much depend. But since right now the way we have written it, it is it related to our surface patch, so we will write it as a surface patch. Okay, so now let us see one example how to calculate it. Okay, so this example is related to something which yesterday last class was yesterday only, right? So yesterday's class I was talking about surface of revolution. We will see that, and then we will go to a sphere. Okay, so what is the surface of revolution? Do you remember, or did you read? I was talking about it yesterday. How you get this surface? So these surfaces are how you get it. Actually, what we do is for these surfaces, we have our z-axis is there, right? And then what we have is we have this x and y. Y is there. So let me write this as a x, y, and z. So what we do is we take a one curve which is inside x-axis. Which is inside xz plane. Okay. So what is this? This is a gamma from some. Let me write it from alpha to beta to R3. Not in R3, we are going to take it into xz plane. So what will be its equation is? If it is in xz plane, what will be equation of this? It will be f of u comma 0 g of u. Do you agree with me? Because y coordinate will be 0 here, right?
Yes, sir.
So it will look like this, f of u 0 g of u. Now what we are going to do is, once I have such a curve, then we are going to revolve it around the x-axis, z-axis completely. Okay. So then in that case, what will happen is you will get actually a surface which will look probably like this. My diagrams are little bad. Not little, more bad are there. So it will look like this. Is okay for you?
Yes, ma'am.
Yes, sir.
Okay. So then actually whatever surface which we get, that is called surface of revolution. So here, so how that, let us write it down. What is that? How that surface will be? Suppose if you take an image of this map. So what is the image of this alpha beta cross? You take a from 0 to 2 pi. Okay, let me write it first, then I'll write it as a surface patch. So what is this actually surface is? This is given by the equation. Let me write it here. So gamma, this is from alpha beta we have, right? Which goes as a, okay. So u belongs to alpha beta and theta belongs to 0 to 2 pi. Okay, and now what will happen actually? Can you tell me what will be equation? What will be this point will be? So what I'm doing is I'm taking this angle theta here from x-axis. So we know that whenever angle is theta, I'll get a cos theta and sin theta, right? See, if I want to find any point on this surface, it will make some angle with the x-axis, right? Suppose if that x-axis is theta, then your coordinate, x coordinate will be cos theta, sin theta with some radius. And what will be that radius? What will be this point is, which is x-axis point is fu, right? So what will be radius of this point?
Fu.
Fu, right? So this is my fu and this is fu. And what about z coordinate? See, right now this is a z coordinate and your height is remaining at the same place. So you will get a g of u only, right? Is this okay?
Okay.
So you will get a f of u cos theta, then you get f of u sin theta, and then what we get it is g of u. Okay, so this is my surface, but certainly this is not a surface patch because I'm taking this close interval, right? So we will start with the surface patch because to define the fundamental form we have to have a surface patch. So let us take this surface patch sigma. This is a map from alpha beta cross. We will take from 0 to 2 pi to this surface S, which takes u comma, actually they don't write theta because v is our notation. Na? So let me write a uv. This goes to f of u cos v comma f of u sin v comma g of v. G of u. Okay. So this is my surface patch. So once I have a surface patch, I need to actually find out whatever what are the what kind of what is the first fundamental fund. But before that, now let me do certain things here. Remember that if this f of u, if it is if it is achieves 0, okay, then that means what will happen is no. Okay, if, right. See, but this surface of revolution, what we need is we need actually this surface to be uh, smooth surface. For smooth surface, what you need is actually we need to find out what is the whether your sigma u and sigma v whether they are whether they are linearly independent, right? That condition we need to check because we don't know right now what is this f of u, g of u, and so on. So, can you just tell me what is this sigma u will be? It is only depend upon, it is a curve, right? So let us write it as a f dot times cos theta. Then you get a f dot times sin theta, comma g dot, right? This will be my sigma u. And what is my sigma v will be? Minus f times, what is this? This will be sin theta. Yeah, cos theta. Okay, you are saying V, no? That is correct. Okay, right. Sorry. So this, let me write here theta, and then when we will write it in this side, we will write it as a V. Okay. So these times, what is this? This will be G. Sorry, this will be 0. Last one will be 0, right? Right. So now actually what will be, if you want to check whether they are linearly independent, what we need to actually, suppose if f becomes 0, then you will be in a trouble, right? Because then in that case, sigma theta will be 0, right? So let us assume that sigma u is strictly greater than 0. Okay, for every u belongs to alpha beta. Another thing, what problem will have, another assumption which we are going to put, and then another thing, suppose if f dot becomes 0 at some point, then what will happen? Suppose if f dot will become 0, then in that case, whether these are going to be linear? See, do you remember that if I want to say that this curve is a smooth, what condition is required? We need actually this sigma u cross sigma v. This should be, or sigma u comma sigma v, they should be linearly independent, right? So what I'm saying is, we will, if, so we need actually first condition is this. Another thing what we need is we need actually f to be regular. So do you remember actually what is the meaning of curve to be regular? That means we want f dot should be also not equal to 0. Okay, these are the two conditions which we'll put it. We will ask, okay, that we want this. And we can actually make little more assumptions also by just saying that this f dot square plus g dot square is a 1. So that means we are assuming that this curve has a unit speed. Okay, unit 1 speed. I think this you might have done it. So these are the assumptions which we are going to put it. Okay, so for our regularity. So what is our assumption is f of u is always strictly greater than 0 and f dot square plus g dot square is 1. Okay, let us put these assumptions on our curve. So now actually let us calculate what is the first fundamental form. So for first fundamental form, what you need is, we need to calculate this sigma u's norm of this. What will be norm of this? We have to add these two, right? So you will get, what you will get it, can you tell me? If I, norm of sigma u square will be d square plus d square plus d square, right? So d square, what you will get it, can you tell me? 1, that is correct. What about sigma v square? So just put it instead of theta 1. So that will be f square, right? So this will be f square. And what will be the dot product?
0.
0, right? Because if you see actually they just get it 0. So because of that, so now can you tell me what is the first fundamental form over here is? So the first fundamental form of this sigma will be E is 1. So you will get actually du square. Middle term is 0. So this is my E, this is my F, this is my, this is my F and this is my G, right? So this is a du square plus f square times g. Is this okay? So this is no.
dv square.
Yeah, dv square. That is correct.
Square dv
Okay. Yes, yes. So this is our form. So now actually, if you so special case of this was a sphere. Okay. So the sphere is, you remember, sphere is a surface which you get it from revolution. Only thing is that we so what is actually a surface? How you can actually write it down? Can you tell me? So this is my x, y, and z, right? So how you get a sphere? You have to take this circle and make it revolve around it. So here only trouble is what actually these 2 points will be trouble, because we are assuming that f of u is strictly greater than 0, right? So just remove it, because we can always choose our surface patch to be a simple. So here actually what will be your gamma curve will be from minus pi. You remember that actually we can just use the one which is, we have already used it. So what is this? This is actually cos, I think it was cos theta. So this was, they denoted by theta, and this was cos theta 0 sin theta, right? Sorry, this is z axis, okay, and this is y axis. That is what I generally write it. And here actually, so this is my fu, I mean f theta, and this is my g theta. So if you take this, what you will get it actually, what is the first fundamental form for sphere? You just use this expression. So what you will get it is, see, this is a theta, and let us, you remember that now I'm talking about the spherical coordinates which we used it very initially.
du
So I'm
square
using,
plus cos square theta dv square.
right, that is correct, correct. Okay, so
d
I'm just
theta square.
using now theta and phi. Okay, so this is what is the first fundamental form for sphere. Okay, and now actually let us see one more example. Let me just quickly go through it, which is again, it was there in the last, what is that? In the last class, I just vaguely mentioned it. So there is a something called generalized sphere. Okay, so what is the generalized sphere? Sorry, generalized cylinder. So let me tell you what is this. So a generalized cylinder, I think last class, Pooja, you missed it, right?
Yes, ma'am.
Right. So let me just quickly recall it. Okay. So generalize. So in general, remember that what is this cylinder? How it is made? You have a circle, and at a circle we are putting all these lines, right? So these kind of surfaces, which yesterday I told you that they are called ruled surfaces. Okay. So generalized cylinder. This is also a ruled surface. So this is a ruled surface. And what we are generalizing here is this curve, which is earlier circle, which is for cylinder, that can be any curve. Okay, so here where, let us write it, where this, so instead of this circle, you will have another curve, which let me denote it by gamma. And what we take it, we take actually all the lines, they are parallel to one particular vector. Okay, so you will have some one particular vector A here. So all lines are parallel to one unit vector. Say A. Okay, and we also demand that this gamma lies in the plane perpendicular to A. Okay, so suppose it can be actually this kind of curve, and your A can be something like this also. Okay, I think I had to put something slant here, but anything. Okay, so these kind of thing, what they call it as a generalized cylinder. Okay, it is right now actually for generalized cylinder we don't put a perpendicular, but in calculating what you call, for calculation of first fundamental form, we will put them perpendicular. Okay, so this figure is actually little what you call, it's not very, you understand now, this curve also will be slanted right now because we want it to be perpendicular to it. Okay. So this is called generalized sphere and then generalized cylinder. And in this case, again, we have to write down what is its surface patch. So the surface patch will be given by sigma uv will go as a gamma u plus v times a. Okay. So v times a means this will be line and this line is passing through this point at only once. Okay. So that is what is this. And we also put again gamma to be, we will assume that this has a unit speed. So once it is a unit speed, that means norm of this is going to be 1. So that is what is our, all these things are our assumptions. Okay. So now can you tell me how to calculate first fundamental form here? So sigma of u will be what? Sigma
Gamma
of u
dot.
will be? It will be just a gamma dot. That is correct. And gamma dot we have, okay, right, gamma dot, and then what is the sigma v is?
A.
Just a, right? It is constant e. So now actually what will be norm of so e is going to be norm of sigma u square, right? So what is it? It is going to be norm of gamma dot square. So which is, I think there is a, are you getting some black patch on my screen?
No, ma'am.
No, okay, good. Okay, fine. So this is 1 then. And what is f is? F is sigma u dot sigma v, right? So sigma u dot sigma v is what actually? See, sigma dot is this gamma dot product with a, but we are assuming that a and gamma dot, they are in a perpendicular. So what will be this dot product is?
0.
0, right? Actually, I don't know what is happening. Some points are not written. So this is f. Okay. So this is 0, and then what is the g is? G is norm of sigma v square. So what is that actually? It is a norm of a. But again, what we are assuming, a is also unit vector we are assuming. So that is 1. So what will be your first fundamental form for generalized cylinder? Can you tell me?
Du square plus dv square.
That is correct. So du square plus dv square, that is our first fundamental form. Square, that is correct. So now actually, so you know, now we understood how to calculate first fundamental form. Then later we will see how to calculate arc length. Is it okay? So what I would suggest to you is you also do one thing. You go back and write down for sphere. We have now different coordinate systems. I gave a surface patches of a different kind, right? Just try to find out what is the surface patch for different. If I take another the surface patches, then what fundamental form you get it? Just try all these things. You should try it. Okay. So now actually let me give you what is the length of the curve on the surface. So we will discuss that. Okay. So how this thing help us to calculate lengths. See, those are very important, right? Because length of a curve, then angle between two tangent and all those kind of things we have to calculate, because in geometry that's what we do. What is the curvature of a surfaces, and if you want to study all these things, we need this fundamental form. That's why, I mean, this form is needed. That's why it is called also fundamental form. Okay, that is the reason also it is called fundamental form. So now actually let us look at what is the length of a curve. So for length of a curve, what we need is, first place we need to have a curve. But since fundamental form is defined in surface patch, what we will do is we will assume our curve to be. So what we are going to assume is we will assume our curve is live inside that surface patch. Okay. So let us do that. So what we have is, we have this u is given, sigma is given. So because of that, I have a sigma u. Okay, and we are, what we are assuming is, our assumption is that if I have this curve gamma, so that will lie within the surface. Okay. So this is my gamma. So whenever we have such a kind of thing, what we do is we first place to calculate anything here, we have to go actually to find a curve which is inside our U. So for that, what we are going to do is we are looking at the sigma inverse of this gamma. So what is the sigma inverse of a gamma? We will assume it as a UTVT. Okay, let me write it down. So this is suppose, and it is given by UTVT. Okay, so so this is our basic things are given to me, and what I want to calculate, I want to calculate the length of gamma. That's what I want to calculate. Okay, so let us see actually how to calculate the length of gamma. So so for length of gamma, you know actually formula for lengths, right? You remember that what is the arc length formula in general? This is from, it will be integration from alpha to beta, and then you will have a norm of gamma, right? You remember this formula?
Integration alpha to beta. Yes.
Is this correct?
Gamma dot.
Yes. Gamma dot.
Sorry, yeah, gamma dot, that is correct. So we essentially need to find out this, and this integration is over dt. So we want to actually find out what is this thing is, right? So let us write it down. So how actually we find the gamma dot of t? Last time also we have done it. You remember this actually? What is this formula is for gamma dot of t? Okay, I'll just see. Sorry. This gamma dot of t, that is equal to sigma of UTVT, right? I'm just writing it. So if you take a gamma dot of t, I mean, we did this calculation earlier, but let us check this again by chain rule. So what you will get it? Can you tell me what is gamma dot of t is? It is u dot of t times sigma u plus v dot of t times sigma v, right? Is that correct?
Yes, ma'am.
Right. So now what can you calculate now norm of this thing? Norm of gamma dot of t? Let us calculate square. So this will be u dot of t times sigma u plus v dot of t. Actually t also shall I, I'll just drop the notation t, okay? So what is this? Sigma u plus v dot sigma v times u dot sigma u plus v dot sigma v. So what you get it? Can you tell me?
U dot sigma u norm square.
Right. And norm of sigma u square is what? We denote it by ue, right? So we'll let it write it as a e. You remember
Yes.
now?
Yes.
Right. Is this Mahensh speaking, is it?
I was speaking.
One second. Sorry, I did not get your name. Can you tell me?
So me.
Okay, Somi. Okay, sorry. And then what is this? Sigma u dot sigma v, we denote it by g. So we'll
G.
just use this notation. Okay. So this is a gamma dot square e. Is this correct? This is g and this is f. EFG, yeah. So then you will get a plus 2 times. What you will get it here? You will get a u dot v dot, and then you will get f here plus v dot square times g. Okay. So this is our gamma dot square. So what is our formula for a length of arc is? So our length is given by, so let me write it. So the I'm writing now formula. So the length of the curve gamma is equal to integration from alpha to beta square root of this e times u dot square plus 2f times u dot v dot plus g v dot square. Okay, and this and square root we have to take it, and this is dt. Okay, so let us calculate one example how to actually calculate this arc length. Okay, so then it will be more clearer to us. Okay, so let me give you one example. Right. So let us take some surface. So the surface we are going to take it is a hyperbolic paraboloid. So what is this surface? This surface, I'm going to just give you a patch. So let us take it from this open interval 0, 1 cross 0, 1 to R3. And what is this surface is given by U comma V goes to U, P and UV. Okay, so this is my surface. And what is my curve is actually, let me take a curve from 0, 1 to, I'll give actually here, I'll give you first on the surface patch, which is T goes to T comma T. So what is happening here is, this is, you have this open box here inside R2. Okay, so gamma I'm taking to be T comma T. So T and this is my curve. Okay, so I'm taking an image of this under sigma inside sorry, this actually did you see this 3D, how to plot the 3D graphs? Just see actually how you can plot this graph. I actually forgotten how it looks like. It looks like some kind of a deviated plane. There are 3D graphs you can plot. You know that there are some online 3D dots you can plot. Have you used them anytime?
Yes, I used GeoGebra long.
Right, exactly. Or actually, yeah. So, or even if you have a MATLAB, just take that or anything. So, anyways, so what I'm saying is, you take actually this. This is an image of this, and then see actually how the surface is. I'm not so good at drawing these things. So I'm just saying that what is our sigma is? Sigma is just an image of this inside R3. Okay. So sorry, this is my gamma. So what is my gamma is? Gamma of 0, 1 to our this surface S, which is image of this. T goes to where it will be T comma T comma T square. Okay, this is my curve in S. And what I want to do is, I want to calculate arc length of this gamma. So how we can calculate? We have to use this formula. Okay, we are going to, what we are going to do is, we are going to use this formula. Okay. Right. So for that, what I have to do is first, first what we have to calculate? We are, yeah.
If we draw T comma T square graph on XZ plane, then T0 T
Don't-
square graph, then rotate it 45 degree along Y equal to X line. This is the graph, no?
I don't know this. Okay, it might be whatever you are saying is true. Don't go to this diagram. Maybe I'll just remove this diagram. Okay. Yeah, it is correct whatever you are saying. I don't know actually how to draw this. Okay, so you just that's why I'm saying just try to draw. Pooja, in 3D graph you see it. Right now we don't have a time. Otherwise I would have drawn it.
Okay, ma'am.
Okay. Right. So now let us see let us see how to calculate here. In our tutorial, we will see actually how that graph looks like and so on. Okay. So now can you tell me how to calculate this? So what will be our E? Can you tell me? So what is the sigma U is? See, this is our formula. So sigma U is what?
10V.
101. Yes, 1.
V. Sigma V is?
01
0,
U.
1.
Right. And so what will be our sigma? So we need to calculate E at this point. Okay. That's why I keep on writing points now for that reason. But let me first write it actually what is E is in general, and then we will substitute this. So what is the sigma U is? So E is what actually? It is a norm of sigma U square. So it is 1 plus V square. Then what is F is dot product of these two. So what you will get it actually U into V, right? And what is the G is?
1 plus
Norm
U
of
square.
That is correct. Good, Sumi. 1 plus u square, right? So now actually we need to find out it at a point t square. So what you get it actually here, what is our E is? E is 1 plus V is a t here, right? So it is 1 plus t square, sorry. I'm sorry, okay. See, this u and v are coming from here, okay, not from here. So what is our u and v is? This is my u actually, and this is my v. So it is a tt. So you will get a E is equal to 1 plus t square. What is f is? F is t square and g is 1 plus t square. Is this okay for all of you?
Okay, ma'am.
Right. So now
Yes.
and what is a u dot? U is his. So u dot is what actually 1
One.
and v dot is 1. So what is
One.
our arc length? Can you tell me now? This gamma is going to be arc length of this gamma is no integration of it is
0
from
to
0
1.
to square root of
1 plus t square,
yeah, tell me, I'll write it.
2t square plus 1 plus t square.
Very good. Yeah. So what is this actually? I think it comes out to be 0 to 1. This is what actually it is 4 times t square. Now, so let me take out 2 out. So you will get a square root of t
2
square plus
4t square.
right.
Or root over.
Right. Right. So now actually, so this integration is of that form, right? Srinanda, do you remember this? What is this? Is square root of x square plus a square or something like that? What is the formula? Do you remember? I don't remember formula.
It was sine.
No, it is something to do with a log. So you
Log.
people
Maybe
just
it is something
yeah.
like log x
1
plus
by
root x square plus a square, something like that.
right. So something actually it's very complicated formula. You just see that, okay? For what is the formula? I'll just give you answer. Just verify that it matches with that formula. Okay. I actually calculated, but I did not write a formula. I directly wrote actually something here. I think it is some p time t square plus half. I mean, I wrote no directly. I substituted. So just check what is this formula is, okay? And then you will get this. I think it is some x times square root of x square plus a square divided by 2, I think. Plus
1 by
a
2a log of
some log of
x plus
something
root
x
over
plus
x square plus a square.
yeah, so yeah, I think like this. I don't know whether this is a or square root a. Is this a? Maybe whatever. Just check this and substitute and find out. Okay, this answer you will get it. So now you understand how to calculate arc length in general if you curve is given to you. Is this okay? Right. So now actually, so this is what is the first section of 6.1. So in that actually 2 things we learned. What is the definition of? So what we learned so far, what is the definition of first fundamental form? And then we learned how to calculate arc length from here. Okay. So now actually, do you remember whenever we study in analysis or something, we will try to study something called isometries, right? So what are these isometries? What are isometries?
Distance preserving maps.
Exactly. So why actually we are bothering over here? We want to actually define isometries of surfaces. Okay. So isometries of surfaces is related to the distance, right? Or arc length or anything. Distance means what actually this arc length is also going to be distance only, right? I mean some sort of distances. So that's why we need actually the first fundamental form is important just because of this reason. Okay, so that it essentially gives me some kind of a distance feeling of a distance. So and once we have a feeling of distance, then we can ask whether suppose if some differentiable map is given to me, whether that is isometry. That means if you have a same arc length over here, after applying function over there, whether I end up getting the same arc length. So such a kind of things are called isometries. And unless and until actually we defined arc length, we could have not done this definition of isometry, right? That's why we defined this first fundamental form for that reason. Is this okay with you? You understood why we are doing this first, what is that? First fundamental form, why did we define?
Yes, ma'am.
Okay, so let
Ma'am,
me
can
write
you
that.
please repeat it? I can't understand.
See, what I said is, do you remember this isometries inside? We generally used to do it for vector spaces, right? Uh, or in analysis also we see what we want to do is forget about all these things. What I'm trying to say is, suppose if I have one surface S and another surface S1, okay, or S and S tilde is their standard notation, right? So let me, okay, here they it is. Okay, see, suppose if I have a function f from S1 to S2, okay, and and suppose if I have I mean, if I want to travel from say point A to point B, okay, so what will be image of this point A to point B? That will be some f of A here and f of B somewhere here, right? Is that okay?
Yes.
Right. So now actually suppose distance, and suppose if I'm since here we don't have a straight line, right? Like for instance, in R3 we defined the distance to be a straight line, right? But we know that suppose for instance if I take a sphere and if I join two straight line, it is not a convex surface, right? So because of that, that straight line is not a straight line on the sphere. I mean, you understand this, right? See, what I'm saying is, in general, if I say isometry means just a distance preserving, that thing won't work for our surfaces, because if I take a
Yes.
sphere and if I take a 2 points and if I join them, that straight line is not at all lying on the sphere. So what I have to do is, because I have to walk on the top of my surfaces, instead of a distance, we have to talk about the length of the arc or length of a path which is joining that point A and B. Okay, so
Yes, ma'am.
if I, okay, so because of that, if I want to say that isometry on the surfaces in general, what happens? Suppose inside R3 and R3, if I'm going, I can just say that you take a isometry means what? Distance preserving map is a isometry. But in surfaces, that isometry will be replaced by arc length is preserved. So suppose if I take a gamma, which is a curve over here, we know that f of gamma, that is going to be curve inside my S2, right? You remember that? What is a curve is just a map from some alpha beta to your S1. So if I compose this with the f, I'll get a curve inside S2. So what is isometry we are going to define is, we will say that if it preserves arc length over here, now we know what is the formula for arc length, right? So if this arc length is same as that of integration over here, whatever dot product of this bigger thing, then we will say that this function is isometric. Is this okay now?
Yes, ma'am.
But now actually there is a one problem is there, because when we defined this arc length, what we said is, we said that this arc should lie within a surface patch. You remember that? That is how we defined it. So I cannot define isometry in general globally, but for local thing we have a word called local. So what we are going to do is, we are going to define local isometry. Means suppose if it okay, so why
First
we
we
have to do
take
this?
any surface patch, then we define isometry.
No, we will define isometry for everything, but we call it as a local isometry. Okay, so you can see, because what we are going to do is, whenever we are going to define this arc length, it is defined for the patch wise, right? See, actually, some of the things now we have to kind of, this book also doesn't talk about. Suppose if you have a surface patch, now you can always divide it into such a way that in the finitely many ways, such that you can add it. So just right now, I'll just give you what is the definition which book gave it to us. Okay, but that definition needs some refinements are needed, but it is kind of out of scope of our this book. But maybe if you are doing some manifold theory and so on, at that time you will take care of those subtleties. I'll just write down definition and then we will see that. Huh? Is that okay? Shall I write definition now? But you understood,
Okay,
right?
ma'am.
What is happening is, arc
Yes,
length should
ma'am.
go as the arc length. Okay. So So whenever we are going to consider our what is that curve right now, just to consider it inside that patch. That's why it is called in fact local isometry. Let me write down a definition, then we will go further. Okay. So if S1 and S2 are surfaces, a smooth map F from S1 to S1, S1 to S2 is called a local isometry. If it takes any curve in S1 to a curve of the same length. S2. Okay, actually that's why he did that. I did not notice it. He wrote it as a slanted. So actually that is necessary because of if you look at a book, he actually wrote it as a little bit slanted because of probably for the same reason. So either you consider your curve to be inside your surface patches, and then for those curves only you check it. Okay, and if it is defined over the entire thing, then you probably need to break it and then add it, but for that one has to make a definition clear. Okay, so that is kind of out of his scope, so we are also not talking about it. Okay, so for time being, whenever we will take a curve, we will take it within that surface patch. Okay, and if a local isometry exists, then we will say that these surfaces are locally isometric. Okay, so what he says that if a local isometry, and one of the example which he's talking about is a function which, okay, today now my this computer is not working properly. I think I need some update. Let me just write this definition and stop, and then we will see it from tomorrow or something. So we see that S1 and S2 are locally isometric. Okay, and one can actually prove that locally isometric will implies local diffeomorphism, and that if that diffeomorphism, if local diffeomorphism is diffeomorphism, then what they call it as it's isometric. Anyway, all these things now I'll discuss it in next class, because I think there is some problem with my computer. It has become little slow. I'll stop now. Satya,
Okay.
right.